So in this video we're finding E everywhere for an infinite sheet of charge on the YZ plane with a surface charge density rho s. We'll start by drawing a diagram. So here's what the infinite sheet looks like. I've drawn it on the YZ plane, and you can see that I've signified the surface charge density with rho s as the question requested. An interesting observation to make is that if you cut this infinite sheet into little pieces, and if you cut it tiny enough, what you'd get is an infinite line. And we know what the electric field is for an infinite line. So if we added the incremental effects of all those electric fields from all these infinite lines that make up the infinite sheet, you can find the electric field at any point. So that's the method we're going to use to find the electric field in general for the surface charge, for this sheet of surface charge. So here you can see that I've cut this line out of the infinite sheet. So here's the line, and I've cut it along the y-axis. That's why I have a dy, because it's a very small line. I'm using calculus here, that's why it's a dy, infinitesimally small. And I use the prime notation because it's the source of the electric field. One of the sources, rather, because I'm cutting many lines across this infinite sheet. And of course the bounds of integration will then be from negative infinity to infinity, because it's for the y it would stretch from negative infinity to infinity. You can also have a line that cuts along the z-axis, so you could have a dz and your line would go horizontally like this. But just to be consistent with the infinite line of charge video that I made earlier, which goes along the z-axis, I've cut it along the y-axis, so you have something similar, like the infinite line will go along the z-axis. This is just a reminder of what the electric field was for the infinite line. And note that there's two things missing. We don't know what rho L is, and we don't know what rho is. Also, another observation to make is this is for just one line, and over here what we're doing is we're making lines that are infinitesimally thin with respect to the y-axis in this case. So we won't just have an E, we'll have a dE to think about. Let's try finding rho L and rho now. So rho S has units of coulombs per meter squared. Rho L has units of coulombs per meter. So to get rho L given a rho S, you can see that we just have to multiply rho s by meters, right? So you have coulombs per meter squared multiplying by meters to give you a coulomb per meter. Sorry for the bad handwriting. So let's look at the picture again now that we have these units, and it'll be very easy to make sense of it geometrically. So here you can see I've written out a much neater solution for what rho L is. That's just rho s times dy prime. This makes sense intuitively because you have a sheet, an infinite sheet of surface charge density rho s in coulombs per meter squared, but you want to find the charge density for this line. Now you've cut a width of this line to be dy prime, and it comes out of this infinite sheet. So it makes sense to multiply the width of that line by this surface charge density for the whole shape just to get the charge density for that line. And the units match up. You'll have a rho L of coulombs per meter and a rho S of coulombs per meter squared multiplied by dy being in meters. So now I'm going to find a point of interest where we can analyze what the electric field is. So we'll start over here, 0, y prime 0. Again, I've used the prime notation because that's the source of the electric field. I've arbitrarily picked the next point. I picked x 0, 0 just because it's one of the easier points to work with. And here you can see the direction vector going from 0, y prime 0 to x 0, 0. Rho, of course, is just the magnitude of this vector. So here I've summarized that. So we found rho L, and we found the direction vector rho is just x minus y prime 0, and it's just standard Cartesian coordinates here, nothing fancy. And here's the magnitude of that vector, which is rho. That's just basic math that we've studied since first year. Now that we found rho, and we know the direction vector, we can find a hat rho. That's just dividing the vector by the magnitude. So we have all the components. We have rho L, we have rho, we have a hat rho. But remember that we can't directly use this equation because that's just for one line. And what we have is many lines, infinite lines across these bounds, going from negative infinity on the y-axis to positive infinity, and they're of infinitesimal with dy prime. So we have to express all of these as a dE, or the effects of all of these components for one of these lines with dy prime will be a dE, or a very small bit of the overall electric field of this whole infinite sheet. And we can find E by then integrating over the bounds of this infinite sheet. So here I've expressed dE, just plugged in all these terms, so I have rho L, plugged it in here, I have rho, plugged that in, already calculated that, and just a hat rho, which we've already talked about before, and I can't just say it's E, it has to be a dE. And now we can actually go on to just solve what this value of E is. So really the hardest part and most important part of the question is finding what this dE is. Everything after this is just math. I know it's not the easiest math to do by hand, but with calculators like the HP50G, it makes it much easier. So that was just what I've written down before in the previous slide, and I've just written the same thing just differently over here. So it's exactly the same thing. I've just separated out the different components of the vector. Why I've done that is because if you observe this component going the a hat y direction, by symmetry, when you integrate over the negative infinity bounds, this integral will go to 0. So we don't have to worry about that at all, and we're just left with this integral over here. Let's actually write that in the integral form. Here you can see the bounds of integration going from negative infinity to infinity on the y-axis. After solving this integral, this is the final solution. For for x greater than 0, you have rho s over 2 epsilon in the a hat x direction, and for x less than 0, the same thing except going in the opposite direction. Here I've just redrawn the diagram of the infinite sheet of charge. For x greater than 0, we have something that goes out from this sheet of charge, some magnitude in the a hat x direction. We found that magnitude to be rho s over 2 epsilon naught, and for x less than 0, the same thing, it goes outwards except the opposite direction to what it was here, so it goes in the negative a hat x direction out from the sheet of charge. That's why I've simplified the answer like this. The and signifies that this magnitude will go out normal to the sheet of charge. Just a helpful takeaway is that in this question, finding the dE is the most valuable part, really, is getting to this point. That has all the conceptual bits, and if you can do that, you've done almost all of the work, really, because the rest you can get a computer to help you out with. In terms of concepts, though, getting this dE is very important. Also, this final solution might be quite useful for midterm questions. You can always build on this and solve more complicated systems just using this answer. Thank you very much, and I'll see you in the next video.